Welcome to today's deep dive. We are jumping straight into just a massive puzzle right at the absolute bleeding edge of generative AI.
Yeah, it's a fascinating one.
It really is. So our mission today for you, the listener, is to figure out why teaming up brilliant, highly capable AI agents often results in them confidently lying to you.
Right.
And paradoxically, why the most obvious solution to this problem, just making them communicate more, actually makes everything worse.
It is a phenomenal, deeply counterintuitive problem.
Yeah.
To understand it, we are working from a 2026 state-of-the-art AI paper by Carson Rodriguez-Saleb.
Good paper.
Incredible paper. It's titled Hallucination as Context Drift: Synchronization Protocols for Multi-Agent LLM Systems. And look, we parsed the dense academic math, the system logs, and the O notations so you don't have to.
Yeah, definitely a lot of math in there. But to really visualize the core issue we're unpacking today, I want you to imagine you are watching a crew team row.
Right.
8 elite athletes, right? Absolute Olympic champions, perfect form, perfect power. But there is a catch.
There's always a catch.
Right. They are all wearing noise-canceling headphones, and each one is listening to a completely different rhythm track.
Oh, wow. So individually, they are executing flawless strokes based on the specific tempo they hear.
Exactly.
They're doing exactly what they were trained to do in isolation.
But the boat is violently spinning in circles, going absolutely nowhere. And usually when you see a boat spinning like that, the instinct is to yell at the rowers.
Right, you think they're messing up.
Yeah. You want to say, row better, fix your form, get stronger.
Form isn't the problem, though. I mean, you could replace them with even stronger rowers, or in our case, more advanced language models, and the boat would just spin faster.
So true.
The problem is their shared reality. They are profoundly out of sync.
And that is exactly the dynamic happening inside the software you use right now. And it starts with a fundamental shift in where we actually place the blame.
Yes.
When an AI hallucination happens, when an AI confidently states a factual error, the entire industry's default reflex has been to blame the model itself.
The assumption is always just that the AI isn't smart enough yet.
Okay, let's unpack this. Because for years, the narrative has been all about fixing the individual brain, right? We think we need better, cleaner training data, or we need to use reinforcement learning from human feedback, RLHF, to teach the model how to sound more helpful and accurate.
Or we force the model to use chain of thought prompting, so it slows down and shows its math step by step.
Right, exactly.
And, to be fair, those model-level improvements have been revolutionary for a single AI acting alone. They genuinely work.
But
this paper exposes a massive blind spot in that approach. We are moving into an era of multi-agent configurations. Think of tools like AutoGPT or Devin.
Oh, yeah.
Where you don't just have one chatbot. You have an entire team of specialized agents collaborating to solve a complex problem, like writing code, debugging, and testing all at once.
And that changes everything.
It does. The researcher points to a massive recent study called MAST, which analyzed 1,600 annotated traces from 7 different agent frameworks.
1,600, wow.
Yeah, and the finding was startling. Interagent misalignment is a massive, pervasive failure category that individual model upgrades do absolutely nothing to fix.
Because it's not the brain of the AI that's failing. It is the interface between the brains.
Exactly. The paper introduces a concept called context drift to explain this.
Yeah.
The agents aren't failing at reasoning or logic.
Right.
They are failing because they are operating from mismatched, divergent internal representations of the shared world state.
So over time, their individual realities drift apart.
Exactly. And the paper breaks this context drift down into 3 specific dimensions.
Let's hear them.
First, there's spatial context. This happens when agents hold different fundamental beliefs about the physical environment or the core data they are manipulating.
Okay, that makes sense.
Then there's temporal context. That is all about time. One agent might be working with a fresh, up-to-the-second API pull from a database.
While another agent is relying on a stale cache of data from 5 minutes ago.
Right. So one agent's current state is another agent's ancient history.
Yeah, that's a disaster. And the third dimension is task context, right?
Yes.
This is where agents accumulate different histories of the workflow itself. It leads to divergent assumptions about what has already been decided, what's been attempted, or what's been ruled out.
Spot on.
To me, it is exactly like a heist movie crew where everyone's watches are completely out of sync.
Oh, I like that analogy.
Right. The hacker thinks the vault is disarmed, the safecracker thinks it's still locked, and the getaway driver thinks they are already running late.
And individually, they are making perfectly correct, logical decisions based on their own watch.
But collectively, they trigger the alarm. They're right in isolation, but together they completely contradict each other.
What's fascinating here is how that shifts the entire paradigm of system design. The failure is strictly in the interface.
Yeah.
Just like with human teams, misaligned assumptions create collective failure. If you and I are trying to assemble furniture, and I think we are building a chair while you think we are building a table.
It doesn't matter how incredibly skilled we are at using a screwdriver.
Exactly. The final product is going to be a complete disaster.
So we have this fundamental problem. If these AI agents are drifting like an out-of-sync heist crew, how do we catch it before they ruin the mission?
Right.
Because unlike humans, they aren't physically looking at each other across a room. Their quote-unquote state isn't a facial expression.
No, it is massive amounts of unstructured natural language. Thousands and thousands of tokens.
Right. We need a way to measure their misunderstanding invisibly, on the fly, without, crashing the system.
And that brings us to the first major technical contribution of the paper. The Context Divergence Score, or CDS.
CDS, okay.
Think of it as a lightweight scalar metric. It is a mathematical tripwire.
A tripwire.
Yeah. Instead of agents constantly reading every single thought the other agents have, which is incredibly computationally expensive, they compress their current state.
Okay, so they condense it down.
Exactly. They take their spatial data, their task history, and their goals, and they write a very short natural language summary. 3 sentences max.
Wait, and what actually happens to those 3 sentences? Because, human language is messy.
It is very messy.
You can't just easily calculate the difference between 2 paragraphs of text.
You map it into math. The summary is run through a sentence encoder, which translates those English sentences into a 384-dimensional vector.
Okay, for anyone who hasn't spent time building vector databases, we need to translate that. Let's make that intuitive.
Sure. Imagine mapping every concept in the universe onto a massive 3-dimensional grid. Similar ideas cluster close together physically on this grid, and unrelated ideas are far apart.
Like apples and oranges are close, but apples and cars are far apart.
Exactly. The sentence encoder does this, but instead of 3 dimensions, it uses 384 dimensions to capture incredibly subtle nuances of semantic meaning.
That is wild.
So the context divergence score simply measures the cosine distance.
Yeah.
Basically, the physical gap in that mathematical space between the different agents' vectors.
And what's the scale?
The score ranges from 0, meaning the agents have identical context representations, to 2, which means they are maximally divergent. They are completely on different pages.
No, wait, I have to push back on this mechanic a bit.
Okay, hit me.
I understand mapping concepts to coordinates, but if they are compressing their entire highly complex internal state, which could be thousands of tokens of chat history and dense API data into just 3 sentences, and then mapping that to a single vector, aren't they risking losing the exact nuances and subtle details that caused the drift in the first place?
That is a very fair point.
Because how can a highly compressed summary catch a subtle, factual error? It feels like trying to summarize a 500-page novel in a single tweet and expecting that tweet to catch a typo in chapter 4.
That is a highly intuitive critique, and it strikes at the heart of why the design of this protocol is so elegant. You are absolutely right that it loses nuance.
Okay. But the goal of the context divergence score isn't to perfectly capture every detail or find the typo. It operates with what computer scientists call O1 overhead.
Meaning what, practically?
It means the compute time remains constant. Whether the agents have exchanged 10 words or 10,000 words over an hour-long task, checking the tripwire takes the exact same negligible amount of computing power.
Oh, I see.
Because if you forced the system to read the entire history every time, which would be ON, complexity, the system would grind to a halt as the task got longer.
That makes total sense.
So the CDS is explicitly just a cheap alarm system. It doesn't need to find the typo. It just needs to detect that your vector coordinates indicate you think the book is a romance, and my vector coordinates indicate I think it's a thriller.
Got it. It's a low-cost smoke detector, not a forensic investigator.
Precisely. And it works in tandem with the second major contribution, the Shared State Verification Protocol, or SSVP.
Okay, SSVP. Instead of agents sharing everything all the time, SSVP sits as a very thin coordination layer between them. The agents just do their work, occasionally bouncing these cheap 384-dimensional vectors off each other in the background.
Totally invisible to the user.
Yep. And the moment that context divergence score crosses a specific threshold, the researchers found 0.25 is the magic number, the system hits the brakes.
So it just pauses the simulation. But hitting the brakes doesn't fix the problem. How do they actually reconcile the drift once they are paused?
The pause triggers a process called context merge. When that 0.25 threshold is breached, the agents involved are forced out of their isolated workspaces.
Oh, so they have to talk.
They must explicitly exchange their full, structured histories, complete with timestamps, and adjudicate the conflict.
I basically have a meeting.
Exactly. They essentially debate the contradiction as an explicit reasoning step. They analyze the logs to figure out whose data is fresher or more authoritative, resolve the conflict, and only then are they allowed to resume the task.
Okay, so we have this cheap mathematical tripwire. But, in the sterile environment of a lab, anything works.
Sure.
The real question is, what happens when these agents face the messy, chaotic reality of a system with moving parts and bad data?
Right. And that's where the travel agency experiment comes in.
It's a scenario I think anyone listening can intimately relate to.
Absolutely. It is the ultimate stress test for coordination, planning a complicated international group trip.
Oh, yeah. Always a nightmare.
Right. So they set up 3 Anthropic Claude Haiku agents. You have a planner agent responsible for the day-by-day schedule.
Okay.
You have a booking agent handling the logistics for flights and hotels. And you have an advisor agent giving destination-specific recommendations for dining and weather.
Nice. And they tasked this AI team with creating itineraries across 8 diverse global cities, right? Places like Barcelona, Tokyo, and New York City.
Yes, very complex logistics.
But to actually test the tripwire, the researchers played the role of a chaos agent. They deliberately injected context mismatches right at the start.
Mirroring the exact kinds of API failures that happen in real production systems every single day.
Right. So they fed the advisor agent weather data for the wrong month entirely.
Tricky.
They gave the planner a truncated schedule, so it thought a 5-day trip was only 3 days long. And the most fatal flaw, they gave the booking agent the wrong airport code.
Ouch.
Yeah. The team is supposed to be planning a trip to Barcelona, but the booking agent is initialized with the airport code for Lisbon.
A perfect recipe for context drift.
Right. Now, here's where it gets really interesting. If you asked almost anyone how to solve this, the intuitive fix is total transparency.
Just tell everyone everything.
Yeah. Just force the agents to constantly broadcast everything they know to each other at every single step so they catch the error. The researchers called this the full broadcast baseline.
Yes.
But when they ran it, the hallucination rate, basically the amount of factual errors in the final itinerary, actually increased by 34%.
It's staggering. It went from a baseline error rate of 0.492 with no syncing at all the way up to 0.658 with full broadcast.
So making them talk more made them drastically worse.
Exactly.
We really need to dig into the mechanics of why that happens. Because how does giving intelligent agents more information result in them making more mistakes?
The paper defines this as the contamination effect. To understand it, you have to look at the underlying psychology, or rather the mechanics, of large language models.
Okay, let's look at the mechanics.
LLMs are, at their core, sophisticated pattern matchers. Their prime directive is to maintain narrative consistency.
Interesting.
When you inject a piece of data into their context window, they don't naturally act as skeptical fact-checkers. They act to harmonize with the given reality.
So when the booking agent indiscriminately broadcasted its erroneous Lisbon data to everyone else, the other agents didn't flag it as an error.
No, they accepted it as a constraint.
Yeah.
There is a graph in the paper that just perfectly visualizes this tragedy.
A tragedy, really?
It charts the system-level context divergence score over time. In the full broadcast mode, where everyone shares everything constantly, that divergence score drops extremely low, down around 0.10.
Okay, so a low score means their vectors are close together. They are in agreement.
They perfectly agreed with each other, but they agreed on a lie.
Wow.
The planner and the advisor, to maintain consistency with the booking agent, simply incorporated the bad Lisbon data into their own context.
So the bad data just infected the entire semantic chain.
Yep. They achieved perfect consensus on a totally hallucinated shared state.
They confidently booked flights to Lisbon, planned a Barcelona itinerary, and didn't flag a single contradiction. It's literally the blind leading the blind.
Exactly.
But when they ran the simulation again, using the new SSVP method, that vector tripwire, it was a totally different story.
Because SSVP isolates the agents until communication is strictly necessary. In the SSVP trials, right at step 2, The tripwire detected a massive semantic gap.
Step 2, so almost immediately.
Yes, the divergence score crossed that 0.25 threshold because the booking agent's vector for Lisbon clashed violently with the planner's vector for Barcelona.
The tripwire caught the mismatch before the contamination could even spread.
Exactly. It paused the simulation and forced them into that explicit context merge we talked about earlier. The agents literally output a reasoning step saying, booking says LIS, planner says BCN. We have a contradiction.
They actually argued it out.
They looked at the timestamps in the initial task prompt, realized Barcelona was the true objective, and corrected the booking agent's reality.
And the results speak for themselves. SSVP lowered the hallucination rate by 5.9% compared to the baseline, completely avoiding that massive 34% contamination spike.
And arguably the most impressive part.
Yeah.
It achieved this while using 58% fewer API calls than the full broadcast method.
Oh, wow. That is huge for compute costs.
Massive. It was more accurate, avoided systemic hallucinations,
Yeah.
and was dramatically cheaper because it only communicated when mathematically necessary.
That is a profound finding for distributed systems, but it raises a critical question about the nature of the tasks themselves.
How so?
Well, the contamination effect sounds terrifying for the reliability of AI. If one bad piece of data can infect a whole multi-agent system, and their natural inclination is to just agree with the lie,
Yeah.
how can we trust them to do anything complex? We have to ask. Does this contamination happen every single time agents collaborate, or is there something uniquely vulnerable about planning a travel itinerary?
That is exactly what the researchers wanted to know. So they ran a cross-domain validation.
Okay, a new test.
They took the exact same underlying mechanics, the same SSVP protocol, and applied it to a completely different scenario, software project planning.
So instead of a planner, a booking agent, and an advisor, you have like a project manager, a developer, and a QA engineer collaborating to produce a software sprint plan.
Spot on. And they injected similar errors. The project manager got a truncated scope document. The developer was told they were building for mobile instead of web. The QA engineer was given stale testing requirements.
So the setup was practically identical to the travel experiment.
It was. The results, however, were totally different.
The baseline hallucination rate right out of the gate was much lower, only 0.188 compared to nearly 0.5 in the travel scenario.
Yes.
But the craziest part is how the full broadcast method performed here. Because in the travel scenario, broadcasting everything caused that massive 34% spike in hallucinations.
Right.
But in the software scenario, full broadcast didn't cause any contamination at all. It actually dropped the hallucination rate to 0.150, which perfectly matched the performance of the highly efficient SSVP tripwire method.
If we connect this to the bigger picture, it reveals a fascinating taxonomy of how information actually works inside a collaborative task.
Okay, unpack that taxonomy for us.
The paper explains this by looking at how beliefs cascade. Think about travel planning. It is a domain defined by cascading shared beliefs.
Right.
Every single detail is tightly semantically linked to the core premise. If the destination city is wrong, then the airport code is wrong.
Yeah, obviously.
If the city is wrong, the weather forecast is wrong. If the weather is wrong, the dining and clothing recommendations are completely useless.
A single erroneous fact at the top of the chain infects every single downstream dimension. It's a systemic collapse.
Exactly. But the software tasks in this experiment were fundamentally different. The knowledge domains were far more orthogonal. They were self-contained.
Okay, I see.
If the QA engineer makes a mistake about a testing protocol or has a stale requirement for a specific feature bug, it doesn't fundamentally rewrite the developer's entire reality of what programming language they're using or what the core product is.
That makes total sense.
The database schema doesn't magically change just because the UI tester has the wrong color palette.
So tasks with cascading beliefs, like the travel planner, are like building a massive house of cards.
I love that analogy.
One wrong foundational card, like swapping Lisbon for Barcelona, and the whole structural integrity of the final output comes crashing down. Because the agents want to harmonize, they just help build the wrong house. You get widespread systemic hallucinations.
Perfectly said.
But tasks with orthogonal beliefs, like the software sprint, are more like building with Legos.
Legos, exactly.
If the QA agent uses a red block instead of a blue block in one corner, it's a mistake, sure, but the rest of the Lego structure is still perfectly sound and functional.
That is a brilliant way to visualize it. And it highlights why SSVP is so critical as a default architecture.
It works for both.
Exactly. When the risk of contamination is high, In those house of cards scenarios, SSVP protects the system from collapsing.
Right.
But even in the Lego scenarios, where contamination isn't a massive risk, SSVP still matches the best performance while saving you 58% on your compute costs by not over-communicating.
Man, that is incredibly elegant. So what does this all mean for you, the listener, as you navigate this rapidly accelerating world of generative AI?
Yeah, what's the takeaway?
I think the core summary here is deeply counterintuitive. In the future of AI, more communication isn't inherently better.
Not at all.
We have a bias toward transparency. We assume that if everyone just shares everything, truth will naturally emerge.
But as AI systems evolve from single, isolated chatbots into complex multi-agent societies, they're running into classic distributed systems problems.
Yeah. If we want reliable AI, we need selective threshold-gated communication like SSVP.
We need a system that knows when to talk.
Exactly. So we don't just have the blind leading the blind into a highly confident consensus of lies.
And the implications here extend far beyond planning a vacation to Barcelona.
Oh, for sure.
This paper is a massive warning sign for anyone building or deploying AI in high-stakes environments, finance, legal tech, healthcare.
Because the stakes are real.
In those fields, a confident incorrect action, like filing a legal brief with hallucinated precedents or making a medical recommendation based on stale patient data.
Catastrophic.
It is catastrophic. We have to stop treating multi-agent hallucination purely as a language model flaw that can be fixed with more training data. That is a dead end. We have to design better interfaces for AI teamwork. We have to build systems that expect drift, measure it invisibly, and force reconciliation before the infection spreads.
It really fundamentally changes how you look at a cluster of AI agents working together on your computer.
It really does.
But, it also changes how you look at us.
Wait, how do you mean?
Because the paper proves that when AI agents indiscriminately broadcast everything they know all the time, they suffer a massive contamination effect.
Right.
Their internal divergence goes down, so they feel like they agree, but their hallucinations skyrocket.
Because their prime directive is to harmonize.
Yeah, so they confidently, happily converge on a completely false shared state.
They prioritize consensus over reality.
And it just makes you wonder, in our own modern world of 247 social media with infinite full broadcast human communication happening every second of the day.
Oh, wow.
Are we doing the exact same thing?
That is a chilling thought.
Are we just a society converging on a low divergence, highly hallucinated shared state? Are we just a boat full of champions listening to our own noise-canceling headphones, rowing in circles, and wondering why the boat is sinking?
A very real possibility.
Something for you to mull over. That's our deep dive for today. Catch you next time.